Welcome to the section on corrective measures. In this section, we shall look at different methods to ameliorate the performance of a model. For our plots, the orange plots will be the validation data plots, or the model's values when the data is validation data, and the other model's values for training data. We start with overfitting and underfitting. Overfitting or an overfitted model is a high variance model, and an underfitted model is a high bias model. Consider that we trained our model over a certain number of iterations. So a model which is trained properly is one which isn't overfitting or underfitting. And this kind of model has both its validation and training loss decreasing steadily until it converges, and on convergence the model presents great performance. But now for an overfitting model, we see that the training loss keeps reducing, but with the validation loss at the beginning of training, but we get to a point where the training loss keeps reducing, whereas the validation loss starts increasing. This simply means that from this point, the model is no longer learning anything new from the data. It actually starts to readjust its weights so that it only suits the training data and doesn't learn anything. Hence the term overfitting, as it tries to over modify its weights to fit with the training data at the detriment of the validation and the test data. And this is a very serious problem in machine learning. Let's take this simple example. Supposing we have this data in which we get as input the number of rooms, and we're trying to predict, or we have as output the house price. So based on the number of rooms, we want to predict the house price of a house. We split our data set such that we have this orange points as the training data, 1 2 3 4 5 6 7 8 orange points, and then the validation data is the white points. Now a well-fitted model could be a linear regression model, which simply looks like this. We see here that this model, or this linear regression model, is trying to learn from the data by coming up with this best fit line, which reduces the distance between the points and itself. And clearly we could see that this best fit line tries to mimic the way the house price varies depending on the number of rooms. Now that we've seen a well-fitted model, let's now look at an overfitted model. An overfitted model will look like this. We see that this model is struggling to touch all the points in the training data. Recall that we are not training on the validation set, so what the model sees is the training data, and so it's struggling to touch all these points. So at the end of the day, we're gonna have our model performing extremely well on the training data, but when given input or when given data from the validation set, it's gonna perform very poorly. Whereas with this well-fitted model, it does quite well on the training, although not necessarily extremely well or as good as with the overfitted model, but it's also able to generalize now when given new data from the validation set. This also shows us that generally when our model is overfitted, it means we've taken a model with way too many parameters, or a model which is too large as compared to the data is being fed with. Now when we have this kind of problem, our goal is to have, or is to leave from this kind of curve to this one where both the validation and the training losses reduce, although not at the same rate, but at least we don't have the situation where the validation loss starts to increase. So this means that we take some measures such that our model now doesn't just readjust itself during training based on the training data, but also learns how to generalize on the data it has been given. Now that said, let's look at some common techniques which we can use to solve this problem of overfitting. The first and most important way to solve overfitting is by increasing the data set. So this means if we are solving a problem and then you have, say, limited data and you notice that your model is overfitting, the first reflex you need to have is that of going out and gathering as much data as possible. As the more data you have, the less your model will be prone to overfitting. The next measure we could take is that of data augmentation. Now, data augmentation simply involves using the same data you have and creating other data points from that data. This is a very common technique in computer vision and natural language processing. Now, in computer vision, this can be done very easily since the inputs are images. So this means that if we have a particular input or we have a given data point which is an image, we could, say, modify the contrast of that image and then use it as a new input. And if we have to do this for each point or each data point in our data set, then we will see that our data set is going to be multiplied by 2. As for each data point, we recreate another data point. But also note that data augmentation or the data augmentation strategies actually depends on the exact problem you want to solve. So for now, we'll keep it at that data augmentation is very important. And based on your problem, you have to choose the right data augmentation strategies. Now, the next strategy we could use is that of early stopping. Now, considering that you train up to a certain point, we could also decide that from this point where the validation loss starts to increase, we could actually stop the training. Now, stopping the training simply means we prefer to work with a model when it was still able to generalize. That is, it was able to give both decreasing validation and training losses. Then the next, we could reduce the model size. Coming back to this example, we will see clearly that this first model or this first line here obviously has fewer parameters as compared to this more complicated model right here. So if we are working with this kind of model, reducing the model size will allow us to work with a simpler model which will be less prone to overfitting. Since the fact that a model has maybe too many parameters gives it the liberty at a certain point to start modifying those weights so much so that they suit only the training data or they suit only the data on which they are being trained on. Our next corrective measure is a dropout technique. Now, supposing that we have this neural network where we have 3 inputs and an output. If after training we notice that our model is overfitting, what we could do is take off some of these neurons. So in this hidden layer right here, we could take off this neuron such that the model now takes this new form where we only have 2 neurons in this hidden layer. Then for this other layer, we could take off this 2 and we're left with that. So when doing dropout, we generally define a dropout rate, which is a value ranging between 0 and 1. In this example, we've taken a dropout rate of 0.33, and 0.33 of 3 of these 3 neurons gives us 1 neuron. That's why we've taken off 1. 0.33 of this gives us a value closer to 2. So we've taken off 2 neurons here. So this will go a long way to simplify our model and make it less prone to overfitting. Our next correction to the overfitting problem is weight regularization. Supposing that we define our loss function such that it takes in the true values of the output and also the model's predicted output values. Instead of relying just on this loss value to update our weight parameters, we can include a regularizer loss for regularization, and then this regularizer has a factor, say lambda, which defines how much the regularized loss will weigh in the final loss value. Typical values in practice for lambda are values like 0.1, 0.01, 0.001. And two common loss regularizers are the L2 regularizer and the L1 regularizer. Let's look at the L2 regularizer and how it helps in regularizing the weights. Now, the L2 regularizer is defined such that for our model weights, or for each model weight, we simply square it and then we add up all these model weights. We also generally also divide this by the total number of parameters, but let's consider that since the constant, we just put all of that as lambda. Now, how does this actually regularize our model? The way this works is, if our model weights are unconstrained, they can feel very free to take in as many different possible values as possible, and this obviously can lead to the model overfitting on the training set. And so, to limit the freedom the weights have to take in all sorts of different values, we could add this weights in the loss function such that as the weight from here increases, the loss will also increase. And since the aim of the model's optimization task is to reduce the loss, this will conflict the idea of the weights taking very large values, and hence restraining the weights to only a certain range of values so that the loss doesn't become too big. And so we end up with a regularized model. Apart from the L2 regularization, which in fact is actually the L2 square, because the simple L2 has a square root here. Now, since we squared that square root, we're left with this. So apart from this L2 square regularization, we also use the L1 regularization. For the L1 regularization is defined such that we have the sum of the absolute values of the weights. But in practice, many times we tend to use the L2 regularization instead of the L1 regularization. Although in some problems, we could use the L1 regularization. And now let's understand why and when we need to use either the L2 or the L1 regularization. The L2 regularization is actually the sum of a quadratic function, which looks like this. This is a simple quadratic function, and the L1 regularization is the sum of the absolute function, or the absolute value of x. We'll suppose that this is x. So here we could plot this out like this. This f of x equals absolute value of x, and this f of x equals x squared. If after a single training step the weights are regularized such that the weight or a given weight becomes itself minus a positive constant mu, where mu is less than w, then the absolute value of mu minus w is the same as mu minus w. And then if we look at the L2, or if we are using the L2 regularization, then the w turns to w minus mu, but the next time this weight has been passed in the loss function, that is passed for regularization, we are not going to have W but W minus mu, and since it's L2 regularization, we will now have W minus mu square. So instead of W, now we have W minus mu, so it becomes W minus mu square, whereas here we have W minus mu still. That's why here we have the L1. That's this the W we have after using or after working with L1 regularizer, and this is the W we have in here, or the value we have in here when we're working with the L2 regularizer. Now for large values of the weights, that's for large values of W, both the L2 and the L1 norms, or rather the L2 and the L1 regularizers, need relatively large values of mu, so that this L2 and L1 regularizers are minimized, and hence will also minimize the loss, since this is the aim. But now when we are dealing with very small weight values, since this L2 regularizer has a square term, and we know that the square of a number between -1 and 1 strictly is less than itself, so we don't need to pick mu values which are as high as W in order for this regularizer here, or the value for this regularizer, to be small. To make this clearer, we could take a simple example. If we have a weight, say of value say 10, then we'll need mu to be in the order around that value 10. So if mu is 8, that's fine. We have for this, for example, we have 10 minus 8, and then for this we'll have 10 minus 8 square. That will be year 2 and then year 4. But as we just said, if our W is say 0.1, in the case where we have 0.1, even if our mu is 0, we shall have 0.1 square, and 0.1 square is 0.01, which automatically minimizes or reduces the value for the regularizer loss without having to pick a value for mu in the order of 0.1. Now if we have to try that for the L1 regularizer, that is picking mu to be equal to 0, we'll end up with the weight, or with this regularizer here, still being the same value we had, that is 0.1, and this doesn't reduce the L1 regularizer value. And so this will cause the L1 regularizer to pick values of mu in the same order as W for both large and small values of W, and this in turn will lead to values of W which are very much smaller as compared to with the L2 regularizer, where even with values of mu which are very small, the L2 regularizer is already minimized. And so in the long run, the values of W wouldn't be too small as compared to if we're working with the L1 regularizer. And so the overall effect of this is that when working with L1 regularizer, our weights tend to be very close to 0, or it's easier for us to have 0 weights with an L1 regularizer as compared to if we're working with an L2 regularizer. And so this means that if we're having a problem in which we could afford to, or if we're working a problem in which we prefer to work with sparse weight values, that is weight values which take or which have many zeros, we will go in for the L1 regularizer. But if we can't afford to have sparse weights, then it's preferable to work with the L2 regularizer. Although in practice, most times we prefer to work with the L2 regularizer. Let's take another example to really illustrate the fact that the L1 regularizer leads to more sparse models as compared to the L2 regularizer. Let's suppose that we have two models, one which uses the L2 regularizer and another one using the L1 regularizer, and that a given weight in the model has a value of 5 initially. So here we have 5 and then here we have 5. For the L2 regularizer, if we pick a mu, that is, if after the optimization step the value of that weight is reduced by 4, then we shall now have a weight of value 1, and in the regularization or in the calculation of the loss regularizer, which is our regularization loss, we'll take a value of W square, which is 1 square, which is still equals 1. For the L1 norm, we'll go from 5 to 1. That is supposing that we reduce this value by 4, so we'll go from 5 to 1, and then we'll have W equals 1. And in the calculation for the regularization loss, we'll have a value of 1, since the absolute value of 1 is 1. Now if we move to the next step, that is, if we reduce the value of this weight by 0.8, then the weight value will be 0.2 for both the L1 and the L2 regularizers. But when this value is passed to calculate, or when it's put in here to obtain the regularization loss, we'll now get a value of 0.04 for the L2 regularizer, and then a value of 0.2 still for the L1 regularizer. We see that although they have the same weight values after optimization, they affect the regularization loss differently. As with the L2 regularization, this weight appears to have minimized the loss more than with the L1 regularizer. And then if we continue, say we go from 0.2, now we remove 0.1, we go from 0.2 to 0.1. For the L1 regularization, the weight is 0.1, and then in here for the regularization loss, we have 0.1 still. Whereas for the L2 regularization, even though the weight is now 0.1, the L2, the regularization loss we have here takes in 0.1 square, which is 0.01. So again, we see that our L2 regularization loss keeps reducing even faster than the L1 regularization loss, although both weights were reduced with the same or by the same value mu equals 0.1. And so if we suppose that we are at the step, let's get back to the step here. If we come back to the step here and we want both the L1 regularization value and the L2 regularization value to be the same, the values of mu for the two have to be different. That is, to go from 0.2 to say 0.01 for the L1 regularization, we will have to pick mu to be 0.199, or rather 0.19 actually, since 0.2 minus 0.19 is 0.01. Whereas for the L2 regularization, 0.1 is okay. And so we see that for the L1 regularization, if we want to have this same effect, that's the loss value calculated to give us 0.01 year and 0.01 year, the weight when working with the L2 regularization is at 0.1, whereas when working with the L1 regularization, the weight now is at 0.01. And so again, clearly we see that it's much easier for the weights when working with L1 regularization to get a 0 value as compared to when working with the L2 regularization. Let's now suppose that during training we have both the training and validation losses which are way above the expected value, or we could say the expected range of values such that we could consider our model to be highly performant. Let's take this example right here. Supposing we have this kind of data showing the relationship between the number of bottles drank and the satisfaction derived. Obviously, we see that as we increase the number of bottles drank, the satisfaction derived starts increasing, and then we get to a point where the number of bottles, an increase in the number of bottles, actually reduces the satisfaction derived. Now, on this kind of model, or rather with this kind of data, if we come up with this kind of simple linear regression model, we'll find that our model would underfit. And this is because this function we are using to represent this data set is way too simple. And using this will yield this kind of curve we see here, where even after training for so many epochs, the loss doesn't drop. And this drop and this stagnation, the loss will be same for both the training and the validation data. Now, in order for us to leave from this kind of plots to this one where both the training and validation loss start dropping, one technique we could use is by simply using a bigger model or a more complex model. So instead of using this model, we could use a more complex model like this quadratic function right here. So instead of using this linear function, we could use this quadratic function. And we could see clearly from this that using the quadratic function will reduce the distance between these data points and the model's function, which in this case is the quadratic function, and hence will lead us to this kind of plot where as we increase the number of epochs, the loss will keep reducing to some acceptable levels, which could lead to a high model performance. Now, you have to also be careful not to over increase the model, because if you over increase this model, we will get back to overfitting. So we have to be careful to choose the right balance between an overfitted model and an underfitted model. Then also we could use a more suited model. A great example of this is what we just saw here, as the quadratic model was better suited for solving this problem as compared to the linear model.